Okay, so we're going to do, okay, Grant, we're going to do limits involving infinity. Infinite limits, limits at infinity, but infinite limits at infinity. Those you've not done. You should be able to do these. Have you tried those? Some people are already trying them. This is the limit as x approaches 3 from the right. Anybody notice anything different about my board?
It's shinier.
It's brighter. I got a new projector. I love it. Okay, do you remember how to do these? You take a number just slightly to the right of 3. Okay, guys? They don't, but we want to be able to graph this. And when you substitute in 3, you get 2 divided by 0. Now, on the exam, depending on the question, you're probably better off saying it doesn't exist or it's undefined. If you give a value of plus infinity or negative infinity, then you have to be right. So what if I go just from the right of this, like 3.0001, this denominator, well, the numerator is clearly positive, but the denominator is positive, so this is going to go to positive infinity. Oops, touch the board, shouldn't do that. But if I go from the left, so I take the limit as x approaches 3 from the left of 2 over x minus 3, like, how about 2.999? Well, the numerator is positive, but the denominator is now. Because this is 3.001 minus 3. That's a positive number.
Oh, yeah, because it's 0.006.
And if you don't believe me, try taking 2 divided by 2.999 minus 3. You'll get a very small number because this is going to be negative, so this is negative infinity. So on the exam, if you say it doesn't exist, you're correct. If you say it's positive infinity, you're wrong if it's looking at this one. So that's the problem with it. They do accept that that does not exist. Right now, I want to know if I were to graph that, which way that curve is going towards that vertical asymptote. So this is a vertical asymptote. Okay? What about the log of x and the tangent of x? Are there any vertical? I even asked if there are any horizontal. What about the log of x? Are there any vertical asymptotes there? Now, you should know what this graph looks like. Okay? Alex, what does this look like? You guys should all be drawing it. Okay, Matt? Drew, do you know what it looks like? Remember how we got the log of x? It's the inverse of something. It's the inverse of e to the x. So e to the x looks like this. So log of x is going to look something like that. So does it have a vertical asymptote, Eric? It does. Has a vertical asymptote at 0. Does it have a horizontal asymptote? No. Some students do think it does. It does grow to infinity very slowly. Like the log of 100 is 12. It grows very slowly. If you graph it, it appears to have a vertical asymptote, but it doesn't. So what happens here to the limit? And the only way I can approach 0 is from the right side of this, and that's going to what? Negative infinity. Now what about the tangent function? Do you remember what the tangent function looks like? It kind of looks like a cubic, but there's vertical asymptotes. Now let's see if I know how to do this. Let's try that. Oh, that's kind of cool. Has vertical asymptotes. And where are they? This is pi over 2 and negative pi over 2. Now be careful. It matters what direction you come into this pi over 2. If you are coming in from the left side of pi over 2, it's going to go to positive infinity. If you're coming into the right side of pi over 2, it's going to go to negative infinity, because guess what we're going to be doing? We're going to be doing the inverse tangent and finding those limits. What I do is I go back to the original function and then switch the domain and range. That's how I do it. But you could remember what the inverse function looks like. I think it's on our worksheet. Okay? Any problems with those? So we have negative infinity, positive. They're not going to infinity the same way from both sides. So you just have to remember that. Well, let's try that one. So I said, now it's different. We didn't do any problems like this. No. What should you put in first? We should always substitute it, right? So it's the log of the tangent of 0. So Grant, what is that? What's the tangent of 0? And the log of 0 can only come from one direction. Just did it. Remember, this is just a number. It's just a number. By the way, it's tangent squared. So it's the log of it. What's it going towards? Can you come in from the left side? It's tangent of x squared. What happens if you square a negative number? Yes, you can come in from the left side because it's squared. But either way you come in, it's going to what? Negative infinity. Yeah, this is the BC stuff. I just think my way through the problems. Now, this is the composite limit theorem, which basically has me take the log of the limit of the tangent. And I don't like to write it this way because you can't put it on your calculator that way either. You have to do it this way as x goes to 0. So that's approaching 0, and it's approaching 0 always from a positive side. So yes, this limit does exist and it's negative infinity. I mean, in that sense, it doesn't exist. But you can tell me if it's positive or negative infinity. This is on your handout. I believe. Now, you have these little theorems, but you know what? I just think through them. Just think through them. Now, if I have 1 over x to the n, if n is a positive number, obviously n has to be greater than 0, then that's going to 0. And this is the inverse tangent function. You either can know it or figure it out. I figure out, you can draw it, I figure it out from the original function, because what does this mean? This means the tangent of negative pi over 2 is equal to x, which is equal to infinity. That's what that means. So if I want to find what this is, then it means the tangent of my angle is going to be equal to x, and x is going to get to infinity. So what angle is that? Tangent of what angle goes to positive infinity? It's pi over 2. But from which side? From the left. That's how I think about it. You could also graph the tangent function, the inverse of it. If you could remember this. This is inverse tangent. This is the way Mrs. Hersman does it. I work with the original function. But as x goes to infinity, this is going to pi over 2 from below. This is going to negative pi over, see, I don't want to do this one.
It's going to negative pi over 2. It's going to negative.
It should be negative pi over 2. I think I have a typo there.
Wait, no, they're exactly the same.
Oh, I just can't see that. Oh! I don't even have my good contacts in. Okay? So this should have been, sorry, this should have been negative infinity. So this one actually goes with that one. So it's just pi over 2. This one goes, as x goes to negative infinity, it's negative pi over 2. So you can remember the graph if you want. Okay, because I didn't see the negative sign. As x goes to negative infinity, Then you're going to come down here, and which one is this approaching? Negative pi over 2. So this one's negative infinity. So it's a negative pi over 2. Sorry. Sorry, just didn't see it right. That's all. Between pi over 2 and negative pi over 2. Right. Then our inverse is a function. If I don't restrict my domain here, then I'm going to have a whole bunch of these green lines, but I'm going to have one up here. Can I grab one? I'm not sure what I grabbed, but anyway, we'll see. So it's going to go up there. And that's not a function, is it? So we restrict our domain to be, our answers will be between pi over 2 and negative pi over 2. That's not pi over 2 from the left. It's negative pi over 2. It is. That's why we better do these. So what about the next one? First, read what it's going towards. It's going towards positive infinity. And if you substitute infinity or big numbers in there, like let's let x be 100, it's going to be, well, let's let it be 10. So the square root of 101 minus 10 over 1. Sometimes they are the same, sometimes they aren't the same. So I can't make that assumption. So we have to do that little math trick that we did last year with limits. And we multiplied by the conjugate of this. I just want to change the form a little bit. This is a trick. Remember doing this? Oh, it's not hard. That may be. Okay, so what do I get? I get the limit as x approaches infinity. See, here's the problem. This is infinity minus infinity. Sometimes it's 0, sometimes it's a number, and sometimes it's infinite. I'll give you another example. Let's do this one first. Multiply these out, and I get x squared plus 1, right? And I pick it this way so I get rid of the radicals in the numerator. They're gone. And it's minus x squared over the square root of x squared plus 1 plus x. So what happens in the numerator? So I get the limit as x goes to infinity. X squareds go away. It's 1 over this thing. Square root of x squared plus 1 plus x. Why is that hard? Is the algebra? Let x get really large. Then it's 1 over a really large number, which is 0. If it goes to negative infinity, it's still going to be 0. Because what's 1 divided? If I have $1 and I give it away to everybody, I try to divide it up and give it away. So everybody in this country gets some. How much is everybody going to get? 0. 1 divided by a big number is getting closer to 0. Remember, that's what a limit is. What's getting close to?
That makes sense. All right. Yeah, no, that's fine.
If it goes to negative infinity, now if they're asking for horizontal asymptotes, you have to look at it from both sides. So let's see. If I'm going to negative infinity, I'm going to get a positive number. And then it's going to be negative infinity is going to be plus well, it's minus a negative infinity. So it's square root of infinity plus infinity. So guess what? It's getting infinitely large. And you could graph it and see for sure. Now, this case, square root of x squared plus 1 minus x, they're very similar. But they're not always going to give you 0. Let me give you another example. What is the limit as x goes to infinity of e to the x minus x? Just think a little bit. Okay, Michael? Think. Let's put in 100. Let's just try a number. What's e to the 100th power? Is it big or small? It's like 3. 3 to the 100th power minus 100. Who's growing faster? They're both getting infinitely large, but one's growing faster than the other. It is. So is this going to come to a limit with a number like this last one did, or is it going to be infinite? It's going to be infinite. So I just think my way through these problems. I made that up so that you realize that infinity minus infinity, because that's what that is not necessarily 0. Might be. It might be 1. And if you want to look at it graphically,
If it was, just going back to if it was x minus e to the x really,
it would be 100 minus e to the 100. Yes. Right. If you take e to the x and try to subtract x off, what's true about the difference between these two functions? Is it constant or is it getting bigger? Does that help visually to see the graph of it that way? If you do it the other way, then you'll see the negative infinity. Okay, Drew? Okay, what about this next one? Now you can graph, you want to graph inverse tangent? I don't do that. Okay, you guys, this is theta. Let's go over this one again, if I already forgot it. The tangent of my angle is equal to x, because it's just a trick I use throughout. Okay, guys? Eric? I want the limit of the inverse tangent function. So I'm going to rewrite it as the tangent, because I understand that one. So it's the tangent of what angle goes to negative infinity. I'll draw my picture. Here it is, and it's all we have to consider is this part right here. So what angle is that going to be? Negative pi over 2. You could draw the picture like Mrs. Hersman does, or you can just work it this way. Anytime I get an inverse trig function, I rewrite it as the trig, because that's the only way I understand it. That's my learning style. Your learning style might be different. If I take this and I inverse it, looks like this. X is going to go to negative infinity. This is bounded below by minus pi over 2. So I'll give you 2 ways to do it. Or you memorize it. You got enough stuff to memorize. Okay, Marshall? Okay, we got a bunch more problems. Oh, we just did that one. Let's go back. Yeah. As x approaches positive infinity, that's this one, it's pi over 2. I can draw it again if you want me to. Now, if I have polynomials on the next one, but always check to make sure your limit's infinity, because, you know, on the exam, they're going to be mixed up. And this is an easy one. Zach, what's the answer to this one? Some of this is new. No? No, you don't want to factor it, because as x gets, okay, guys, as x gets large, huge, talk about our budget deficit if you want. I don't know if they talked about it in the debates last night. But you know what? This doesn't matter as x gets large. It looks like this. Now, some of you have memorized tools for that, but you know what? Yeah, but you know what? It's easier than that. It's 3/5.
Don't even try to tell us not to use that. I remember Mr. Johnson last year, he explained the entire lesson, trying to explain that. I crossed the entire thing out once we realized the whole Bob stop.
Easier than that. The question is, what if it's this? Hey, you guys. Guys, what if it's this? This looks like, well, this is equal to 3/5 of x. And if x is going to infinity, that's going to go to infinity.
what if it is 3x squared over 5?
Okay. Now, some of you, guys, if you're going to be talking, I'll ask you to leave. Some of you have memorized things, but honestly, this is 3 over 5x. If x gets big, this is going to 0. I don't want to memorize. You have so much stuff to memorize. Just wait. We haven't done chapter 8. There's tons of stuff to memorize there. Just think. It's much easier. I don't know. Okay, you guys try this one. I don't believe it's 0. Find. Limit is an operator. Okay, you guys? Compute means do the operation. That's an operation. I know there's no plus sign. It's not an adding operation. It's a limit operation. Find out what this value is getting close to. This is x squared plus 1. It may be 0. I don't remember the answer.
plus x.
Trevor, do you have a answer to this one yet?
And then like some weird stuff happens with that.
Well, you need to do it. I don't remember. It might be 0. Seems awfully similar to the other one. But don't, you know what? Don't ever assume. That's right. I mean, it could be 0. I don't know until I do it. Okay, what do we get in the numerator? We did x squared minus 1. Oh, is it the same one? Oh. Okay. Oh, well, what if we put a minus sign in there? Will it change that? X squared minus 1. It'll still probably be 0. Yep, it's still 0. Well, I'm glad we got the same answer both times. Because if we didn't, we'd be in trouble. Of course, my mother balanced her checkbook once by hand and with the calculator. Got the same answer, but the answer was wrong. Now, how you managed to do that, I don't know. Okay. I can't see that. Oh, it's a negative infinity. Careful with that one. And 9 is even harder. What I do is put a number in. X equals negative 10. So it's an see, exponentials are different. A negative exponent doesn't make it a negative number.
It makes it 0.
So it's e to the negative 10, which is 1 over e to the 10. So they shouldn't be too hard, but they might challenge you a little bit. This one's a fun one. Find the limit. It's an operator. It's like saying compute 2 plus 3. It's exactly the same thing. Now this is as x is going to 0. Makes a difference which side you come into 0 on.
So it's negative. It approaches 0.
From the negative side. So this, let's say, it's 0, so let's make x equal to negative point. Well, let's just do negative 0.1, which is negative 1/10, right? Okay, Oren? Sorry. So what are we going to put in here? So it's e to the 1 over negative 1/10. So it's e to the negative 10, which is 1 over e to the 10th, which is 0. I know what it looks like. We can look at it. Want to look at it? Hey, shh. Let's do is the next one on the sheet? How about we do the limit as x approaches 0 from the right? Let's do that one. Okay, shh. Let's put in 1/10. X equals 1/10. This is just a reciprocal. So it's e to the 10th. I know, but I want you to realize that this is going to what? Infinity. So from the left, it's going to 0. What does this function look like? Have you looked at it? Shall we look at it? It's kind of an interesting function. Sorry, they fixed this and now I can't do this. Oh, I'm not recording? Thought I was. Too late now. Okay, you guys? Let's graph that. Y equals E. I can now see this. To the 1 over x. 1 divided by x. I should have cleared things out. Okay, Eric, question? Now I'm going to zoom it 4. Interesting looking function. Is that what you expected? Not what I expected, but it's coming in here and it's going, and I could try to zoom in, and it looks like it's going to 0, and that's going to infinity. I wish this worked. It's annoying. Let's zoom in on it. Now, I like the Inspire zoom better, but that's okay, we're not on. And I suspect that you have some questions on homework as well. Do you guys remember how to zoom in? Oh, look at that. It looks like it's changing concavity there. You know what I can do? I can change. Well, it looks like it. I'm going to go to second format, and we're going to turn my labels off. I'm also going to turn my coordinates, my axes off. You guys do know that you can do this. I don't need the labels. I thought it was something else. Huh. There, now we can graph it. It does change concavity there, doesn't it? And that's getting infinitely large, so I'm not seeing anything from the right. It's kind of interesting. Strange function, I think. Question? With my new projector, it kind of blinds me. Now here's one where you're going to make a mistake if you just substitute in infinity. So if you want to do this algebraically, I just think it through, Eric. Put it away, please. Well, we haven't done this one. What is this?
Infinity.
Why?
11 is negative infinity. Because if you put in like 6, it'd be 36 minus 6 would be 30.
Or you could factor out x, so it really looks like x squared as x gets really large. So yes, this is going to go to infinity.
And then is the next one negative?
I don't have to look at it.
Yeah, it is.
Is that it's a positive infinity, right? So all I look at are the highest degrees. So it's looking like minus x squared over x. So yes, it's looking like minus x, so it's negative infinity. And then I might check it with some numbers. But is that the last one? Now, what about questions on the homework? Does that make sense? This one? All I care about is the x squared, the highest degree here in the numerator, and the highest degree in the denominator. Easy to miss the minus sign. Oh. Oh. Okay. Boy, 4. Okay, there you go. This was horizontal asymptotes. How do you find horizontal asymptotes? They're the limit as x approaches what? No, horizontal. Infinity, it's the end behavior. But what you also check? Negative infinity. So you're going to have to do 2 limits. Give you a chance to try that. This is 2008, number 19, multiple choice. They threw it out because everybody got it wrong. Find the horizontal asymptotes. Find the limits as x goes to infinity and negative infinity. When they ask you this question, you must do both. Well, it's not a polynomial, so I can't use my rules, all those silly rules that you learned. It doesn't apply. So I want the limit as x goes to positive infinity. Well, it doesn't work for exponentials. Now, when x gets really large, do I care about the 5 and the 2? This is 2008, multiple choice number 19. No, it's 2 to the x over minus 2 to the x. What is that? Negative 1. Now, that's the more obvious one. You must check it. Just because you have a horizontal asymptote of negative 1 on one side doesn't mean you have it on the other. Think about a graph. You know, if the horizontal asymptote's here, it could have done something like this. Or there could be another horizontal asymptote. Okay? So what do I have to do next, Grant? Of 5 plus 2 to the x over 2 minus 2 to the x. Now, this is where I'm going to put some values in. Okay, Drew, so what do I get? This is right off the exam.
I think that one's 0. I'm going to go with 0.
Well, let's try x equal to negative 10, for instance. It's 5 plus 2 to the negative 10 over 2 minus 2 to the negative 10. Grant, will you not do that? Thanks. Right? Because this is 5 plus 1 over 2 to the 10th. And this is 2 minus 1 over 2 to the 10th. And so basically those are 0, so it's 5 halves. So be careful. They had to throw it out because very few people got it right. I personally think they should have kept it in there and just adjusted the score a little bit. But they actually threw it out. I was very surprised at that. Pardon? You see, they're exponentials. And the problem with learning the little thing with the polynomials, it only applies to polynomials. That's a problem. No, that'd be full points. This was multiple choice, though. Now, do you have questions on any of the homework questions? I expect to see questions on them. If you're having a homework quiz on this coming up, I think we'll do it Monday because tomorrow, well, we might do it tomorrow. But Monday's a work day, so Monday is a really short period. No, it's either tomorrow or Monday. Let me see how long the lesson is in 2.6, which I haven't submitted. Let's prove that we have at least one real root. I find where what's 0. Nick, how do I do this? It's not the squeeze theorem. Starts with an I. Intermediate value theorem. And you know what? Intermediate value theorem only applies for a single function. These are 2. And they ask you to find where they intersect. But the problem is I don't even know where to set my window. I have no idea what to do with my window. However, if I subtract them, 100 e to the minus x over 100 minus 0.01 x squared, and I put this into my y value, and if it's going to have an answer, if they truly do intersect, what should I get for an answer? If they intersect there, and I subtract those y values, what should I get? 0. So I'm really looking for the zeros here. So to prove that I actually have a 0, I will evaluate my function, how about at 0? F of 0, because that's easy. That's 100, that's e to the 0, right? Minus 0, so that's positive, right? Now, what other value would you maybe want to try? 100, I like 100. Why did you choose 100, Zach? Then this is e to the negative 1. I just want it to be negative, though. So it's 0.01, and it's 100 squared. Coming back 2 will give me 100 divided by e minus 100. Eric, I need you not to be chit-chatting. If you're not interested, that's fine. Is that negative? It's 100 thirds minus 100. I don't care how big you make it. It doesn't matter. I just want to show that there's at least one. Okay? So this is less than 0, and because my function went from positive to negative, I know it had to be 0. Do I care about the y values when I graph this? No. Now remember, those of you who didn't know what to do, once I helped you with it, it was okay. Now I need to get my axes back on, otherwise I won't be able to see anything. And that's my domain. I don't really care what my range is. It's not going to matter. And I can give you another example where you want to do that. So I want to clear this out, and it was really not a very pretty looking function. So it's 100 e, I hope I did my calculations right, to the negative x divided by 100. I would go to the table values if I really wanted to see what that looked like. Minus 0.01x squared. Now, it might not have been negative, so then I would have to go play with it more. So my window, I want to go from 0 to 100. I don't care what the y values are. That's good enough. There it is. Wouldn't be easy to see when I've guessed something that big. Let's find it. Second, calculate. There's other ways. If you want me to show you other ways to find it, I want the 0 for doing this from. Now I just type in 0 and I type in 100. So it's going to look in there, and there it is. No, that's not it, because I could have more than one 0. So it always says a guess. I just ignore it. There it is, 70.3476. So have you ever graphed 3 to the x and x cubed? Where do these intersect? Well, obviously, there's an obvious answer. No. 3. But and we're going to graph it. But I'll show you what happens when you graph it. This is a problem. First off, one thing is I have to figure out where that answer is. I know there's 1, but I know there's another 1. So I'm going to do y equals, I'm going to clear that out, 3 to the x, okay, Grant? Whoops. 3 to the x and x cubed. And why don't we just zoom it decimal? I'm still not going to see it. Because what's the value going to be? It's going to go up to what? 27. So let's make the window go up to 30. Now, I'm okay with my domain, it looks like. And I'm going to show you what happens with zoom fit. It doesn't work. Now, okay, Will? Can you even tell it intersects twice? Yeah, clearly. I could zoom in. That's a lot of work. I don't think I want to do that. So that's the problem. And so I'm going to go back to this, and let's zoom fit it on that domain and to show you that it doesn't help. So zoom fit works a number of times, but not all the times. Zoom, and I don't know where zoom fit is, and I never use it. Rarely. I mean, I will use it once in a while. You have to have the domain first. Okay, it's pretty worthless. So instead, I'm going to go here, y equals, and I'm just going to subtract. So I'm just going to go up over here and do minus x cubed. It doesn't matter which one goes first. X cubed. Where's the caret? Oh, you get used to one calculator, and then you get another one. Okay, I'll leave the same window. It's okay. Well, actually, I don't like it. Ooh, we know it's between 0 and 4. So let's change my window to be 0. Zoom fit is not fun. Look at the values there. 4 And then let's just make this negative 4 to 4. Because I only care about a 0. Actually, let's make it negative 1 to 1. I don't care about that. I want to be close to the axis, not far away. There it is. Now you're telling me that that's harder to find the zeros than it is to find the intersection points? Okay, Sam? It's easy to find the zeros. So if I do, are you curious where it is now? Now, when I find the zeros, and I'm going to type in 0 to 4, and now it says guess, because there are 2 zeros. So I better tell it which one I want to look for. So we'll put in 1, because it'll give me the left one. Okay, now this uses Newton's method of finding zeros, and sometimes Newton's method fails. It just failed. So what I can do instead, well, we can still do the second, calculate. Let's type in 2 and 4. 2, 4. And my guess, if I guess 4, I'm going to be over there. So I don't want to do that. Let's type in 2. There it is, 2.47. We used to teach Newton's method. We don't do it anymore because the calculator does it, so what's the point? But it's 2.47. The other one's 3. They're so close together you can't see them. And you can find the y value for that too. How about homework questions? Another one. There was another one you said. Oh, that's the monk. I might challenge you to do this. So you have a monk, and he is leaving the monastery at 7 a.m. and takes the usual path to the top of the mountain. So there's the mountain. He starts here. He's going to go up. Okay? That's at 7 a.m. Grant, do you know how to do this? And at the top, takes the same path back, arriving back at 7 p.m. Oh, they even say use the intermediate values theorem. It says use the intermediate value theorem to show that there's a point on the path that the monk will cross at exactly the same time of day on both days. Okay, you guys, Zach, how are we going to do that? Duncan, how am I going to do that? That problem. That's the monk problem. No, no vectors. It says use intermediate value theorem. You don't have to find any equation. It's easier than that. I don't know what the equation is. It depends on how he walks up there. But it doesn't matter how he walks up there. Will he pass the same place at the same time? Does it say at the same time? It says, will he? He's at a point on the path. The monk will cross at exactly the same time on both days. Yeah. Why? You get to prove it. Grant? Eric, have you figured this one out yet? Okay, Eric. You need to think about that. I'm going to leave it like that. It's at the same place at the same time. It's not on the answer sheet, I don't believe. Keep in mind, I just used the intermediate value theorem for the last couple examples.